back to another video lecture for section 2.8. Here we're talking about function composition. We're in unit 3. So function composition we need to recognize is just another way that we can operate within function notation. And so far in the course we've talked about transforming a function using a constant. So we know that we can reflect a function given some f of x by putting a negative sign out in front of it, basically flipping the sign of everything, which will have the effect of flipping the graph over. Or we can plug in negative x and then see what results to our function, and that has the effect of flipping it from left to right. Now so far all of our transformations that we have, reflections, translations, and stretches, these are all one function and one or more constants being added or multiplied or changing the parity of the function in order to reflect, translate, or stretch one particular thing. But sometimes it might be necessary for us to consider two or more functions and how they operate in conjunction with each other. And so that's where function composition comes in. The only difference here is that the transformation that one function has on the other is not always as obvious as just a single constant being added, subtracted, or multiplied, or divided. So when we have two different functions, we can compose them in several different ways. Of course, we can add two functions together to produce a new function, and then the new function has various properties just depending on what terms were added to it. We can subtract functions, because if we can add them, we can obviously subtract them. We can multiply and divide functions, which is these two notations right here, f times g of x or f divided by g of x, or vice versa. And then the last one that we have is probably the one that will take the most amount of time to get familiar with, and that is actual function composition. We denote that by f, this little open circle, which is like saying the word of, so f of g of x, or we can compose them in a different order and get completely different functions out of it. So it's important to note that there are some properties that we're maybe familiar with from the very start of our high school algebra classes, like the commutative property, that only apply to some of these classes of functions. For example, f plus g of x is going to be the same thing as g plus f of x. F times g of x is going to be the same thing as g times f of x. But when we start subtracting or dividing, or we start composing functions, then that commutativity goes out the window. So these kind of behave in strange ways compared to what we're used to. So we need to learn how to operate with them so that we can take two functions that we know and compose them together to get something new, and then we can evaluate what the graph does based off of the results. Okay, so the big idea in this lesson is just we can use an operator like add, subtract, multiply, divide to produce a new function from two or more old functions. And then we have this new operation which is the composition operator, and we can produce really strange graphs using that, and I'll show you how that works here in just a second. So moving into some examples, let's look at the easy stuff first. So suppose that I have this function f of x, which is defined as 3x minus 4, and I have this function g of x, which is defined as 2x squared minus 1. Okay, so both of those are they're functions that we should very easily understand what they look like and how they behave. This is a parabola that's been stretched by 2 and moved down 1 unit. This is a straight line that's been stretched by 3 and moved down by 4. Or in other words, this one's probably the easiest for us to get a handle on because we've been doing straight lines since Algebra 1. But what happens if I choose to add these things together? So in part A, I'm asked to find two different quantities. What is f plus g of x? And then what is f plus g of 0? And I want to show you two different ways that we can do this, because there's kind of a quick way and then there's a not so quick way. So sometimes you'll be asked to find what f plus g of x is. This is a new function. You're going to get some expression out beside this that has some x terms and some constants all composed together. Whereas f plus g of 0 says find f plus g of x and then plug in 0 for x and see what results. We can also kind of shortcut this thing where I'm doing f plus g of 0. I can shortcut that if all I'm asked for is to plug in a certain number, and I can do that in actually almost all of these cases. So let's start by finding f plus g of x. In this case, what I'm told to do, think of this like it's a set of instructions, and it tells us how do I put together a new function from the old ones. Well, I take whatever f was, 3x minus 4, and I'm going to add whatever g was. G was 2x squared minus 1. And notice that this is just a single line expression, which we're used to dealing with. We know that we can distribute, combine, and solve things. We're not really going to solve anything here because I'm just looking for a function out of this. The result is a function. So all I'm going to do is I'm going to do the distribute and the combine steps, but I'm going to stop after that. So notice that 2x squared has nothing that it combines with. 3x has nothing that it combines with. But minus 4 and minus 1 are both constants, and so I can add a negative 4 and a negative 1 together to produce negative 5. And here I find that f plus g of x is 2x squared plus 3x minus 5. And that's it. That's all there is. When you're asked to find a composition of x, you will get an expression like this. It will have x's in the answer. When you're asked to do something like this, where it says plug in 0, well, the first step, if you want to do this the same way every time, we can find f plus g of x, and now all I have to do is plug in 0 for x. Well, if that's 0, the whole thing is 0. If that's 0, the whole thing is 0, so what am I left with? I'm just left with negative 5, and that's the answer right there. That's it. Now, we can also shortcut this if you want. I can do that without ever finding what f plus g of x is, and I'll show you that with an example here in just a second. Now the second one asks us to do something a little bit different. We have f and g just kind of run up against each other, which reads f times g of x. So what I need to do here is take everything that was in f, 3x minus 4, and I need to multiply it by everything that was in g, 2x squared minus 1. You notice we have two binomials that are being multiplied together, and so I can rewrite this down here. I can just FOIL this thing out and get a result. So if I multiply the first term times the first term, I'm going to get 6x to the third. I multiply the outer term times the outer term, I'll get minus 3x. Inner times inner, I get minus 8x squared, and then of course last times last, I have minus 4 times minus 1, which is plus 4. And this thing, even though it's a little bit out of order, that's it. That is f times g of x. That is the result. We're done. We just have to look at it and say, can I combine any of the terms? Well, no, because there's an x to the third, x to the second, x constant, none of those combine. That's it. That's the result. Now, if it wants me to plug in 4, all I have to do is stick 4 in here and see what comes out. So I'll have 4 to the third power, which is 64 times 6 is a big number. And then I'll subtract 12, and then I'll have minus 8 times 16 plus 4, and all I have to do is like actually stick the numbers through there and get my result. So I'm going to do that real quick. Pull up my calculator. So I've got 4 to the third power, which is 64, times 6, which is 384. Okay. So this part, that's 384. Minus 3 times 4, which is 12, minus 8 times 16, which is 128, plus 4. Okay, so I guess altogether that is 388 minus 140. So 388 minus 140 will give me 248. And that's all there is to it. Okay. Now suppose that I was just asked for something like, I guess this would be C. Suppose I was just asked for something like f minus g of 2. And it doesn't want me to find f minus g of x. Well, you can do this problem by going ahead and finding f minus g of x and then plugging in 2, which is perhaps the slower of the two ways to do it. Or we can recognize that since we're dealing with function composition here, I can just find f of 2 and g of 2 and subtract the 2. So if I plug 2 into f, I'll get 6 minus 4, which is 2. And if I plug 2 into g, I will get 8 minus 1, which is 7. So f of 2 was 2, and g of 2 was 7. So 2 minus 7 gives us negative 5. And that's it. And we can even do this with multiplication. Suppose that I wanted to find f times g of 1. This is the same thing as finding f of 1 and g of 1 and multiplying the results. So f of 1, plug 1 in here, I get negative 1. Plug 1 in here, I get 1. So negative 1 times positive 1 is negative 1. And notice that I didn't have to go through the effort of finding what f times g of x actually was. Although, if I wanted to, I could figure this out and then just plug 1 into here. And we'll notice we get the same result. If I plug 1, because f times g of x is this expression right here, I'll underline it in this green color. F times g of x is this green underlined expression, so if I plug in 1, I'll have 6 minus 3, which is 3, 3 minus 8, which is negative 5, and then negative 5 plus 4, which is negative 1. So there's two different ways to do this. You can do it kind of the tricky way, if all it's asking you for is to plug in a number like 2, 1, 7, stuff like that. But you have to do it the hard way if it's asking you to find f times g, f plus g, f minus g of x. You have to come up with the expression for it in that case. So it's kind of up to you how you want to do it, but there's a bunch of different ways that we could. Now with division, I do need to point out that we run into kind of an interesting situation with division. Division is already something that a lot of people feel a little bit uncomfortable with when you start seeing x's in the denominator, as most of you experienced with the rational functions part of Unit 2. So we have to be pretty careful about this, but if it just says find f divided by g of x, the answer is actually pretty easy to find. F divided by g of x, we just take everything that f of x was, 3x minus 4, and we divide by everything that g of x was, 2x squared minus 1. And if this doesn't simplify, well then there you have it. That's it. That's all there is to it. Okay. So you just follow this set of instructions here to compose a new function, and that's really all there is to it. You just do what it says. Now, I'll clean up the board and I'll come back with the difficult examples, the function composition operator. Okay, so we have a new problem set here involving a new f of x and a new g of x. So they've said set f of x equal to x squared minus 3, and g of x is 2x plus 1. And we're supposed to find the expression of each of these compositions. So notice here we're not plugging in any numbers. Since we're not plugging in any numbers, we're not going to be able to use that little shortcut trick that we talked about in the first example. You actually have to do the operation and come up with the result. So first one, we're supposed to take f of x and add g of x to it. Okay, so f of x was x squared minus 3. G of x was 2x plus 1. Okay, so if we're going to do our distribute and combine steps, remember we don't actually solve for anything here because we weren't asked to. We weren't asked what the roots of this particular expression are. We're just saying what is the expression that results. So I can notice that x squared is alone, so is 2x, but then I have this minus 3 and plus 1, which are constants, and so I can combine them. Minus 3 plus 1 leaves me with minus 2, and this is my result. X squared plus 2x minus 2. F times g, I'm asked to take everything in f of x, x squared minus 3, and multiply by everything in g of x, 2x plus 1. So again, when you're multiplying binomials, we want to remember the FOIL method. First times first will give me 2x to the third. Outer times outer will give me plus x squared. Inner times inner minus 6x, and last times last minus 3. And at this point, I'm going to look at it and I'm going to say, can I combine any of the terms? And we have descending exponential order, x to the third, x squared, x, constant. Nothing can combine, so that's my result, that's it. Now here I wanted to show you something that Pearson has a tendency to do just to try to trip you up. A lot of times they're given f plus g or f minus g or whatever, but remember that the order that you do this in actually kind of matters a little bit. So this one is actually g over f. Don't go in the reverse order, f over g, or that would be a wrong answer. So g over f says take everything that was in g of x, 2x plus 1, and divide it by everything that was in f of x. And once I've written them like that, that's it. That's all we know how to do at this point. We would simplify this if we could, but that's a topic for next unit. So we have some additional examples here. Example D wants us to find g of f of x. Now this is the function composition operator. This is a little bit different. A lot of people think that this is like multiplying g and f together, which would just be the result from part B right here. If you were multiplying g times f in the opposite order, it's the same thing, because it doesn't matter whether I write this one first or write that one first. But that little O is not a multiplication symbol. You have to actually compose these things together. So what is composition? Composition means I'm going to take the function that's on the outside most, and there's kind of two ways to teach this, so I'm going to show you what I call outside in. And the outside is like this part right here, the very first one that you read, that's the outside. The inside is the next one that you read, and then the next one, and then the next one, and then the next one, if there are next ones. In college algebra, there's usually only one or two of these. So we're going to take the outermost function here, we're going to write it down, and everywhere that I see an x in that function, I'm going to take it out, I'm going to leave kind of a big parentheses, okay? So g, what did g say? G was 2x, whoops, plus 1. Drop my chalk. So notice that I've taken the x out, and I said x, but I left a parentheses. And that's very, very deliberate. Because now what I'm going to do, I've taken the outside function, I'm going to move to one of the inside functions, which is f, and I'm going to plug in f of x where that parentheses was written. So f of x, x squared minus 3. So now I need to distribute and combine. Again, we're not solving because there is nothing to solve. We're just finding an expression here. So if I distribute the 2 into this parentheses, I'll have 2x squared minus 6 plus 1. And then combining, we can notice that this 6 and this 1 are both constants, and so I can simplify. I will have 2x squared minus 5, and that's the result. Okay, so what you need to kind of understand about what is happening here, try to move a shadow in front of that so we can see it for just a second. Sorry, the glare is pretty bad on that side of the board. That's unintentional. Okay, so what we need to see here is that with adding or subtracting or multiplying or dividing these functions together, they kind of behave in a way that we would expect. If I add an x squared term onto 2x plus 1, I'm going to get an x squared term in the result. If I multiply an x squared term times a 2x term, I'm going to get a 2x to the third term. Function composition does stuff a little bit differently. You notice that I started with a linear expression, I composed it with a quadratic expression, and I got a quadratic expression out of it. It didn't like magically turn it into a cubic or some other thing. It kind of does something a little bit more strange than just addition or subtraction or multiplication or division. It has weirder effects on the functions. And the other thing I wanted to show you is that the order that you compose the function in matters. So a fifth example, let's find f of g of x. Okay? So the same procedure is what we're going to follow. We just have to do it in a different order because the instructions are in a different order. So we take the outermost function, f. F is x squared minus 3. And that is x squared minus 3. Remember, we're going to omit the x's and leave a parentheses, which is what I've done here. Then I'm going to plug in the next function in the innermost function, g. So g is 2x plus 1. Well, now you notice I have some really weird stuff written down. I've got 2x plus 1 squared. So that's 2x plus 1 times 2x plus 1. So I need to expand that. I can either write that as 2x plus 1 times 2x plus 1, or I can use an expansion formula. For right now, I'm going to write it as 2x plus 1 times 2x plus 1. So you see that when I square a binomial, I have to FOIL it out. So this is like 2x plus 1 times 2x plus 1 minus 3. And then, of course, first times first, I'll get 4x squared. Outer times outer, I'll get 2x. Inner times inner, I also get 2x. And then last times last, I get plus 1. And then I had that minus 3 on the end there. Okay? So now I need to combine. And you'll notice that I have this 2x term that are both common to each other, and so they can be combined. And I have this 1 and this 3, which can be combined as well. So altogether, I'll have 4x squared plus 4x minus 2, and that is my answer. So hopefully what you can see is that what we got when we did g of f of x is completely different than what we got when we did f of g of x. And that's a little strange. And furthermore, this composition operator is maybe not as straightforward as just adding, subtracting, multiplying, or dividing. So you gotta be kind of careful with the composition operator. Always make sure that what you're doing when you see that little O, it's like taking the x out and replacing it with the other function, and that's the way that we find a function composition. Okay, if you can do these things, then you've got section 2.8.